Okay, let's give this flipped classroom thing a shot here. So what we're going to be working on today is we're going back one section here because chapter 5 is a little jumbled in my opinion. So we're looking at section 3 for this, which is called the fundamental theorem of calculus. Probably a pretty big name if it says fundamental and it has the name of our course in it. And there's really two parts to it. We have to start off with the assumption, supposing that f is continuous on an interval a to b. If that's true, we could define a function g of x that is equal to the integral from a to x of f of t dt. If all of this is true, then we must have that the derivative of g of x equals f of x. Secondly, the second part of the fundamental theorem is an integral from a to b of f of x dx equals big F of b minus big F of a, where f is the antiderivative of f, or I should say big F of little f. Same notation there. Now, you should read this again, try to think through what's going on, but today, kind of strangely enough, we're focusing on part 2 of the fundamental theorem of calculus. We'll come back to part 1 tomorrow, but we're going to be looking primarily at part 2 here. So, part 2 is what we'll use all the time. Let's do a handful of examples here, and then tomorrow in class we're running back, just looking at a bunch of examples ourselves. So we could be asked to integrate ex from 1 to 3 with respect to x. So let's look at what part 2 is saying we need to do. If that's true, we need the antiderivative and then of the b minus the a terms. So if we're looking at this, the antiderivative of e to the x is, in fact, e to the x. What happens with this integral sign to say that we took the antiderivative is it kind of flattens out as we pull it down here. Notice the dx is gone as well. That just means we have taken the antiderivative with respect to x. What this now kind of notation, this solid straight line afterwards means, we still need to evaluate it at 3 and 1. So, like up here it says b, the second one minus the first one. So we need e of 3 minus e of 1. And we can't really simplify or do anything here, so that actually is good for our answer. Let's think about what this means in terms of like the context of everything as well. E to the x, which hopefully we all know, is this exponential function. We just found the exact area under the curve from 1 to 3. So for this e to the x function, the exact area of this segment of the curve is e to the third minus e to the first. Great. Let's look at a couple other questions. Sometimes they'll give you them in like word problems. They could say something like, find the area under the parabola x squared, and let's say from 0 to 1. So this is a question we've done a bunch already. But since they kind of have written it in spoken word here, we have to know we want the area under the curve, so that's an integral from 0 to 1 of x squared, and it's with respect to x. That's why we need that dx at the end. Actually taking this antiderivative here, goes x to the third, the 3 comes down in reciprocal form, and we still have to evaluate it at 0 and at 1. So we should have 1/3, 1 to the third minus 1/3, 0 to the third, which just comes up 1/3. And we've done this and come up with this result in a bunch of other ways in our class as well. Let's look at a couple more integrals. We could have one that's like this. An integral from 3 to 6 of dx over x. This notation freaks people out initially, because if you look at our prior examples, dx was at the end. It still is here. It's just how you want to think of it. So sometimes questions may write them in this form, but really we can just think of them here. So we need the antiderivative of 1 over x. This is the one we were talking about today. It's x to the negative 1, but really we just have to think of this as becoming ln of x. And we need to evaluate this from 3 to 6. So that's the ln of 6 minus the ln of 3. If you remember any of our ln rules, we can combine these. Subtraction becomes division, which is really just the ln of 2. So a bunch of different ways to do this. And I think I only want one more example for us today. And the last one would be an integral here from -1 to 3 of 1 over x squared. And I'll write this kind of our normal way with dx at the end instead of kind of in the numerator. So normally when we'd go through this, maybe we'd want to think about, oh, I don't like it like that form. I'm going to write it here. The exponent goes up 1, right? I add 1 to make it a -1. That now needs to be flipped in front. -1 to 3. This is really like -1 over x, 3 -1. If we're continuing this work up here, that's -1 over 3. It's always minus, and that's based off of our second part of the fundamental theorem. It's always subtracting. But it's important to keep in mind if your function's negative, that may throw some issues in there. Minus, oops, it helps when I write the right number here. This is a -1. So we really have to keep in mind all of our negatives here. Right, those two negatives make a positive. It's still negative here, -4/3. And you may be thinking, oh, we can have negative areas, which we can. That would then incorporate area that's underneath the x-axis. However, I'm going to say that this answer here is wrong. Classic. Got you to write down the stuff, hopefully, even when I'm not there. Now, why is this wrong? We followed everything else we did here. I'm going to draw a graph of this to help us even kind of visualize it. Because remember, we're thinking area under the curve for this function. 1 over x squared, if you're trying to go through your brain and remember, this is what I like to call it, that volcano function. And maybe now you're hopefully seeing why we're having an issue here. If we're going area under from -1 to 3, that'd be from here to here, and we're shading all this in. The issue becomes up here, right? That goes up to infinity. That's probably going to be an issue. And you're saying, well, you gave us one that doesn't work already. Remember the first part here. We have to suppose that it is continuous from A to B, that interval. Are we continuous from -1 to 3? Nah, we're not. So because of that jump, we are not able to do this actual integral. You cannot include 0 in this integral. So the answer to this would be that this does not exist because it's not continuous on the interval. Okay, we've looked at a bunch of nice examples here. If you want to get a head start tomorrow in class, where did I write these down? What we're going to be doing in class, the opposite of homework, since this is your homework now, is we're looking at number 19 to, which one did I have up here for us? 37. So it's like 18 of them, but a lot of them at the beginning are really of this level. It's just used to getting it in your hand. Oh, and it helps if I say the section. We're in 5.3 here now. Okay. Hopefully this worked out great for everyone. See you tomorrow in class.